Go ahead.
What is being shared right now? I can't tell. My screen just
Does it
it's
have to do?
paused. What? Okay, let me try again. This
Yeah,
is
go for
off to a good start.
it.
All right, can you see my presentation?
Yes.
All right. So today we're actually starting quantum computing. Finally. So we had to get through a lot of background first, but now we're here. So I think I was the one who presented on this, but a few weeks ago, we said that a state vector is represented in the standard basis as a 0 ket and a 1 ket added together with each has a respective amplitude. And I also went over some very elementary quantum gates which you apply to a state vector. And you can see them here, the poly x, poly y, poly z. They also are written like this. That's a terrible sigma, but they're also written like that sometimes. But in Nielsen and Chuang, they just write x, I think. So, all right. So there's more than just the poly gates. There are, I guess, an infinite number of potential quantum logic gates, but we're not going to go over all of them. So here I just showed you some of the really basic ones. So the Hadamard gate, you can sort of think of it as entanglement inducing gate, the phase gate, and the pi/8 gate, which is like a rotation. And since we're dealing with state vectors specifically, that means we're actually dealing with pure states, which means when you visualize the state on the Bloch sphere, it's going to be on the surface. So in other situations, we might be dealing, I don't think in this book, but in other scenarios, you might be dealing with mixed states, and those would have the vector on the Bloch sphere would actually be within the sphere. It wouldn't be on the surface. Not really relevant to what we're going over right now. I just thought it was worth mentioning. So here's some more gates. This is just a generalized rotation gates about each axis, and you can see that they're the sum of the identity and their respective poly gate, obviously times some amplitude. And then in general, if you just want a single qubit logic gate, you can represent that by e to the I alpha times the rotation about a unit vector. So that's what n hat is. And then actually calculate that, you take the components of the vector, each vector, and multiply it times the respective poly gate. Just it's identical to the rotation about the x and y. It's just for a generalized unit vector. So you can rotate anywhere on the sphere using this formula. So there's a lot of exercises in this chapter, which are, I think if you're unfamiliar with quantum gates, it'd be helpful to do because they're not hard, but they are very enlightening. So I just picked one that I thought was relatively simple. So we want to show that poly x times poly y times poly x is equivalent to the opposite of the poly y gate. So if anyone wants to do that of the two people here. I have more space if you'd like to write.
I got this, guys. I got this. Wait, how do I write? Annotate, right? Yeah.
Yeah.
Okay. All right. So what do we want? X, Y.
X equals negative y.
Equals negative y. Okay. So we got 0, 1, 1, 0, 0 minus I, 0, 0, 1, 1, 0 is equal to, do the first matrix multiplication, minus I, 0, 0, I, and that is 0, I, minus I, 0, which is minus y. First part done. All right. And then I guess you want something like this maybe?
Let me check.
Yeah.
Yeah.
Okay, so we have the first relationships. Let me really erase all that. I probably just would have been worth just clearing everything, but whatever. All right. Okay, so x ry of theta, that's x times cosine theta over 2 I minus I sine theta over 2 times y. And then there's an x on that. Crap, I can't minimize that. There's an x here. And that's equal to, so we distribute the x. Cosine theta over 2 is a scalar. So we get x times x, or x times I times x, which is x squared, which is the identity, I think. Yeah. Minus I sine theta over 2. Now I have to erase this x. We get x times y times x, which we just showed was minus y, so this becomes plus y. And the sign is an odd function, so we can pull the minus sign inside. And the cosine is even, so cosine of theta over 2 is the same thing as cosine of minus theta over 2. And so this is ry of minus theta. Yay!
Yay, you did it. Oh, you cleared the annotations. That's good.
Yeah.
All right, so does that make sense to everyone here? So,
Roy, how come whenever you give a talk and you give really cool talks, where we have to, work on things with you, and then it's just like the four of us.
It's okay. In case someone watches the recording, I'm still gonna pretend like it's normal. So, so next up, I think I'm technically not supposed to present on this, but there was not enough material, unless we just wanted to do exercises the whole time, which I guess is fine. But next up, we're looking at multi-qubit gates. So in the past, if you looked at the matrices, it's a 2x2 matrix, but the actual size of the matrix is 2 to the n, where n is your number of qubits. So, for example, controlled NOT and controlled U each use 2 qubits. And I think this is our first time seeing a circuit diagram. So I'll just briefly go over it. So this would be, say, like, this would be the first qubit, and this would be the second qubit. So basically in a circuit diagram, each qubit has its own line, which I believe is identical to just a normal circuit diagram. All the ones I've seen are like this as well. The actual gates notation is sometimes a bit different, but not glaringly so. So So once you move on to more than just a single qubit, you can actually get control control gates. So two that basically encompass pretty much everything, I guess, is the C naught gate, which is very common. You'll see, and in a C naught gate, the you have a control qubit and a target qubit, and the control qubit, which I've highlighted, if the control qubit is 1, the target qubit will be flipped, but if it's 0, it won't be flipped. And you can apply that more generally just with a controlled unitary gate, where the unitary will be applied only if the control is 1. So I guess you can sort of look at the matrix as this is sort of weird to write, but like sort of like that. Obviously, the matrix is the best way to represent the actual state, but each you can sort of think of it as 4 individual blocks in the case of a 2-qubit diagram. So next we are looking at some 3-qubit diagrams, the Toffoli and the Fredkin gate. So Fredkin gate, oh, I didn't go over the swap gate, but this is this symbol means you swap the states. So the Fredkin gate is just a controlled swap. And with Toffoli gate, you actually have two controls and 1 target, which is the direct sum of the control gates product. So basically, if they both need to be 1 in order for something to be added, because 0 times 1 is 0. You can see the matrices right here. So here's another exercise where you get to generate the truth table of the Toffoli gate. So is everyone familiar with what a truth table is?
Yes.
Okay. So if someone would like to go, except for Marguerite, who I can hear now but is not allowed to go.
I think I could do this without writing it if somebody else could write it.
Yeah, I can write
but
it.
I will. Okay. So supposedly that's control not. So if you send in 3 zeros, you get 3 zeros out. You send in 2 zeros and a 1, you get what?
Here, can someone else draw? My mouse is really messed up.
Roy just drew a turd on the screen.
Right now?
My mouse is really
bad. I'll write it. Okay, so you send in 3 zeros, you get 3 zeros. Okay, what next?
Yeah, you send in 001, you get out 001. You send in 010, you get the same thing out. 011, you get 011, and then next counting number 100, you get 100 out. 101, you get 101. Sorry, I'm trying to remember how to count in binary at the same time. and then you get to the 2 states of interest, right, which are the 110, which goes to 111, and you have 111, which goes to 110. And I believe that is all of your states.
You did it, and you did it in the right order too.
Exactly the right order.
Beautiful. I can participate.
So we can verify that. But
well, I conveniently wrote everything to the right of the correct answer. We're on a roll today.
So that you could do this truth table like this for any gate. But in general, I think the matrices are usually easier, but I guess the truth table is more it's more apparent what's actually happening. uh, let's
I
see.
actually really like to use this notation a lot when I'm trying to figure out what a circuit does.
Yeah, yeah.
Circuit, the direct sum notation here. I use it all the time. But anyway, yeah, let me clear this.
All right. So the last thing we're going over, which, wow, I am really blazing through this. I don't know what else to talk about. I'm sorry. Uh, so measurement, we talked about this earlier. Every measurement is a positive operator valued measure, which is distinct from just saying a measurement. Measure is something else. Just to be clear. But when you're dealing with a quantum logic circuit, at the end of the circuit, you obviously want to have something you can actually look at. Like, just having a qubit is worthless because you don't know what it is. So you want to measure it eventually. So there's two main techniques when you're dealing with quantum logic circuits, and the first is the principle of deferred measurement, and what that basically says is any measurement, you can delay it until the end of the circuit, and it'll be equivalent to having it earlier. So I just had this is an example from the book where on the left is just, I don't know what is up with this graphic. There's a bunch of things wrong with it, but I think this is supposed to be filled in, but
It was correct. So if you do a not and then do a control and then do a not, it's the same thing as asking.
oh, it's doing nothing.
Well, no. Okay, so what does the solid dot say? It asks you whether your qubit is 0 or 1, right? And if it's 1, then it triggers something. If it's 0, then it does nothing. If you put an X in front of it, then it flips the qubit. So now the control is asking, is it 0 or 1? If it's 0, do something. If it's 1, do nothing.
Oh, okay.
And then when you do the X again afterwards, it converts it back to the original state. So this is correct the way it is.
Yeah, I think I just haven't seen this like hollow circle before. So that's just the opposite of a control.
Yeah, exactly.
Okay.
Exactly, yeah.
All right. Well, anyways, as you can see from the diagram, these two are equivalent. So let's see. Oh, and the other measurement technique is the principle of implicit measurement. So what that basically says is that you don't have to measure everything. You can just assume at the end of a circuit that has been measured. And I probably should have put this on an earlier slide, but what's at the bottom of the page here is just some common notation. So you have your state vector, it's a qubit, so it's a solid line. You apply the measurement, and then since you measured it, it's no longer quantum. So then in quantum computing, we represent a classical bit with two solid lines, which usually are not that thick, but whatever. I made the lines very thick on accident, but and you can still do things with the quantum bit. I mean, classical bit, obviously, just not quantum things. I guess. Yeah, that's the end. We could do an exercise on our some principles of measurement. I don't know if you guys would want to.
Let's do it.
Okay, they were a bit more advanced, that's why I didn't include them. But let's see, let me pull up the textbook. I think one of them was verifying that the principle of deferred measurement is valid. So let me just pull it up. That would be a fun one.
So that principle basically says if you have a measurement in the middle of your circuit, then it's possible to move it to the end by replacing it with some quantum operations.
Yeah, okay, so exercise 4. No, that's not what I wanted to look at. Exercise 4.32. So suppose rho is a density matrix, so it could be a pure or mixed state, describing a 2-qubit system. Then you perform a projective measurement in the computational basis on the second qubit. Let rho naught be the density matrix which would be assigned to the system after measurement, and show that rho naught is equivalent to applying the, I don't know the proper term for this. I see this all the time, but the outer product?
Yeah.
Okay. Yes, show is equivalent to the density matrix sort of sandwiched by the outer product. Are outer products, or would this be an isometry? The rho P0 and P1?
Let's see. They are, no. They in general change the length of a vector, right? So it can't be an isometry. They are projectors though.
So then we want to show the reduced density matrix is not affected by the measurement. That's the important part. All right. So there's not a lot of blank space. Let me make a paint.
Density matrix which would be assigned to the system after the measurement by an observer who did not learn the measurement result.
Okay, let me share. Now we can actually work on it. So we want to show that.
That looks like a P phi with the curly hair.
Okay, so did we even go over the form of a density matrix? It's fine. So a density matrix would just be, correct me if I'm wrong here, but oh, oops.
Dude, I do that all the time.
Yeah, the expectation value of 1. Or maybe this is the density matrix, right?
Let's see. So what does it say? It's a 2-qubit system. Do we need?
Oh, would it be multiplied together?
I think we might need like the outer product of 0, 0 with 0, 0 and then 0, 1 with 0, 1, and so on. Like, so there's a lot of these.
Oh,
So
yeah,
maybe
I shouldn't articulate it out like this.
Okay, maybe we can just kind of try to reason with what the answer should be. So we want to show if we make a measurement, but we don't learn what the measurement result is, and then the density matrix is this rho prime guy. So how does not knowing the measurement affect the state after the measurement is made?
Well, I want to say it doesn't disturb the state, but then that's just what this is saying. It's not really proving it mathematically. I think since they asked for the trace, they expect us to actually get rho specifically.
Oh, wait. The projector, okay, we're only measuring the second qubit. I see. Okay, so, oh God, I really don't want to have to write out this whole thing. So since we're only measuring the second qubit, all we do, I think, is apply the P0 and P1 operators to the second qubit of each component of the density matrix, if that makes any sense.
Yeah.
And so whenever 0 comes into contact with a 1, that term cancels. Whenever it comes into contact with a 0, then that term just remains the same. But let's see, why do we have to do both and sum them up? Oh, because we're doing a measurement in the computational basis. And so we want to figure out whether the second qubit is a 0 or a 1. And so the only projection operators are P0 and P1. And I think we have to use one of the postulates that tells us the state after the measurement.
Oh, in the book?
Yeah. I can also go grab my my solutions that I worked out.
The state after the measurement is whatever the measured state was, normalized by the previous sum of coefficients. Basically, it's the renormalized state that you just measured. I don't know if that's helping at all.
Okay, let me go grab this bad boy.
Zach's consulting the solution manual. I mean, that he made, but still.
If y'all need some Nielsen and Schwalm solutions, hit me up. What was the number again?
Is 4.32.
Okay. All right, so here's what I have written. So if outcome I were to occur, so if the resulting state is I, either 0 or 1, then the state of the system after the measurement would be pi times rho times pi over the probability of pi, or sorry, the probability of I. All right, so that's just one of the postulates, but in the density matrix form. So if the observer learns nothing from the measurement, the state must be, okay. So then the state is rho prime equals P0 rho P0 over the probability of 0. And we get that with probability P of 0, so we multiply it by P of 0. Sorry, probability of 0. And then do the same thing with 1 and add them together. But then the probabilities cancel.
Yeah.
Okay, so I think, yeah, the idea is that when you learn nothing from the measurement, the result is a mixed state, right? You get result, you get the outcome I with probability P of I, and you get the you get the outcome 0 with probability P of 0. You get the outcome 1 with probability P of 1. And so what you have is a mixed state, and the state is P0 rho P0 over probability of 0 that just normalizes it with probability P of 0, and then P1 rho P1 over the probability 1 times the probability, which is 1. That's just the definition of a mixed state. And then they cancel and you get rho prime. So you want to think about the second part, or?
Well, the trace is defined as this is the trace, right?
Yeah. Well, we have a 2-qubit system, so I guess it would have to be ij rho ij, and then you sum over ij. Oh wait, no, it's the partial trace we want. Yeah.
I
So
always forget the definition of partial trace.
so you're only tracing out the second component. So this is fine the way it's written. You just have to make it clear that you're only doing the second component. But I think I figured it out with a much easier method. I didn't have to expand it. Okay. So the partial trace of rho prime, well, we already figured out what rho prime is, so we can just plug that in.
Would you use the cyclicity of trace?
That
Would you use the cyclicity of trace, or?
Eventually, yeah. First you use the linearity. Yeah, there you go. You got it. Yeah, so then use the cyclicity.
Oh, oops.
Oh, I wasn't even paying attention.
I obviously wasn't paying attention either.
Okay, but what do we know about?
These multiplied together are just themselves, so then you would just get.
Yeah. Yes, whenever you have a projection operator, it squares itself.
Yeah.
Right.
Why did I do that? I mean, it's the same thing, but.
Okay, so now combine the sums back together. but P0 plus P1 is what?
It's the identity, right?
Yes. Ta-da!
Well, I wouldn't have thought to do that. I would have tried expanding it all out.
I can tell from the eraser marks that I tried that as well. So you're not alone.
Yeah, so this is the deferred measurement principle. We did it. Or I guess Zach did it, and I wrote down what he said.
I more like I did it several months ago, and then we all cheated. You want to do one more?
Let's see. What, Dominique? What exercise would you like to do?
Let's see. Let me open this guy up again. It's a really long problem statement. That one. Let's do 4.35 maybe.
Okay, let me find 4.35. .35.
Yes.
So prove that n hat dot sigma squared, that one.
Wait, prove what? We might have different.
Let me share my screen so you see what I'm
Okay.
looking at.
Yeah. 4.35. Like 4.35.
Oh, 35.
Yes.
I was thinking section 3, problem 5.
No.
Let's see.
There you go. I guess I have to read it for Marguerite. So the goal of the problem.
Thank you.
Well, the problem is to show that measurement commutes with controls. So a consequence of the principle of deferred measurement is that measurements commute with quantum gates. Oh no. Measurements commute with quantum gates. I gotta move my thing now.
And there's a bunch of diagrams about it commuting with quantum gates.
Yeah. So, okay, wait, hang on. Consequence of the principle of deferred measurement is that measurements commute with quantum gates when the qubit being measured is a control qubit. So whenever you have like a control U and then you have a measurement on the control qubit, you can always move that measurement to be in front of the control qubit.
Yes.
That's what we want to prove.
I don't understand the difference between the second two.
It's just notation.
Oh, okay. I was like, it looks exactly the same to me, but so is what they're saying, we want to write out the matrix of this and then apply a projective operator, or we could apply an operator and then apply the controlled unitary, right?
So
I know a way to do this, but it involves like writing down the controlled gate in a particular way, where it becomes clear that its action is an identity, and then it trivially commutes. But
I
Yeah,
did
I
it.
don't know.
I did it like the very brute force way. I just kind of wrote like an arbitrary state. So psi 0 is like a times 0, 0 plus b times 0, 1 plus c times 1, 0 plus d times 1, 1. And I just tracked it as it went through the circuit.
Yeah, so you can always write like a control gate as like identity on your control qubit plus non-identity, like whatever your unitary that you're implementing on your target, you know, either identity or that on your target. But if you're not measuring on your target and you're measuring instead on your control qubit, and if you were to think of it like you traced out your target, then all you have is an identity on your control, and everything commutes with the identity. And so that's a very slapdash way to do it. But it requires like knowing how to write an arbitrary control unitary in terms of its action on individual qubits, which I feel like is not the way Nielsen and Schwalm wanted you to do it.
I think, Roy, you have the right idea. Like you want to take this matrix and just apply it to some pair of qubits. You know, maybe just assume they're in a pure state for now.
So then you just. I always get the matrix of the pure. The matrix of the pure state is the one with off-diagonal elements, right? Or is that the mixed state?
I was just going to use like the pure state notation, like the Ket notation, but
oh, that's even better. So then, when you apply a measurement, what is going on? It's just, oh, it's writing in white, that's why.
well, how good that does.
So here's a pure state.
that works, yeah.
And
Oh, wait. Actually, I think you can have off-diagonal elements when you have a pure state.
I always get it.
Yeah, you can. Okay, all right. Don't use density matrix.
Just a pure state is a density matrix if it has only one eigenvalue. So if you diagonalize it, a pure state has only one non-zero element. But if you're not talking diagonal, I don't think you should like try to write out a matrix of a pure state.
So we're using this unitary U, and we don't know what basis it's in, right? So I think we should just assume that it's the computational basis, and we don't want to do any diagonalizing. So what I would do is, if we're assuming everything's a pure state, then I would, here, let me annotate, I guess. I'll write in red so we distinguish. So we'll start off with like a state A 0, 0 plus B 0, 1 plus C 1, 0 plus D. That's not crap. Your pictures are in the way, guys. Mouse, there we go. Okay, got it. 1, 1. Mm-hmm. And so what happens is this becomes A 0, 0 plus B 0, 1 plus C times 1 times U0. Mm-hmm. And U1. And then we make a measurement on the first qubit, which was the controlled one.
Yeah.
And we have to figure out from the postulate what happens then.
Here, I'm gonna scroll. It's gonna mess up your notation.
Awkward.
So this means that measurement after is the same as measurement before. So measurement. Here, I'll just write it. I'll just copy it. So then we apply the outer product, right?
I think it might be easier to just argue what the resulting state is. Right. So you can see, so you make the measurement of the first qubit on the computational basis.
Mhm.
It's going to be either 0 or 1. So let's take the first case.
So if it's
Suppose,
0, the
yes.
output is going to be A0 plus CU0, right? Plus B1, sorry.
Yeah, it's just the A00 plus B01 over the probability of getting 0, which is A squared plus B squared. Right. So here, I'll write it, I guess. So if we measure 0, then the resulting state, psi twiddle, is equal to A00 plus B01 over modulus of A squared plus modulus of B squared. So that's my postulate, right? After I make my measurement, if I get 0, then this is the resulting state. And the probability of getting this is the A squared plus B squared part on the bottom. If we measure 1, then the resulting state is C 1 tensor U0 plus D 1 tensor U1. And once again, I have put the pictures in the bad location. And then we divide that, we divide that by the probability of getting this measurement, which is modulus of C squared plus modulus of D squared. But this guy can be written as, let's see, 1 tensor with C, oh, actually, I can pull the U out too. 1 tensor U applied to C0 plus D1 over the modulus of C squared plus the modulus of D squared. Okay, so we have to compare this now to the other case. Yeah. So what happens if we make the measurement first?
If we make the measurement first, it's going to be one of those two. Because it's either 0 or 1, so then you'd eliminate the other two.
Okay, so let's pretend it's 0 first and see what happens.
Then it would just be A0 plus B1 over A squared plus B squared.
Right. Yeah, exactly. And if we get 1, We get 1, we send the 1 in to the control gate, and the control gate says apply U now.
Mhm.
And so we get
Just
exactly
apply
what's,
U.
yeah, we get exactly what's written there. And so the two are equivalent. Yay! I mean, you also have to argue that the probabilities are the same, but you know, they are.
So we did some fun exercises. Thank you, Zach, because I didn't know how to do those.
Nielsen and Schwang have some like really fun ones. They have some really enlightening ones, and then they have some really infuriating ones.
I just want to chime in that this is incredibly frustrating to listen to because I know how to solve it much simpler than Zach was describing, but I have to write it down. And I just want to go on the record. And this is so annoying.
I like everything being mathematically rigorous. All right. I don't like intuitive arguments.
It would have been. It would have been.
But I think
This would have been like 3 lines.
I think a good homework problem for us all is 4.36. And then let's all come up with separate circuits and see who gets the best one.
Construct a quantum circuit to add 2-bit numbers x and y modulo 4. Oh, that's fun.
Yeah. Let's see who can get the smallest one.
All right.
Anyway, yeah, homework.
I'll post that.
Sounds good. All right, so let me go ahead and stop the recording.